empty tank, no water inside the rainwater harvesting tank. This represents the phenomena of when the owner firstly installs the rainwater harvesting system, or the owner is performing maintenance on the rainwater harvesting system. So the tank storage will be 0. So we assume a 0 tank storage for each month, because we wouldn't know when will the owner install the system or when will the owner perform maintenance. So we assume an empty tank size for every month. And for each month, there will be a tank volume. And within all this tank volume, the maximum value will be taken as the required minimum storage volume. There's a reason why we take the maximum value here, but we still regard it as the required minimum tank storage. There's a reason behind it. We look at how does the algorithm goes. We start at month January. The empty tank start at month January. At February, we have excessive harvested rainfall of 84 meter cube. So this 84 meter cube of water will be kept inside the tank. At month March, the water inside the tank is 84 from previous month, and this month we have excessive harvested rainfall of 219. So the total volume will be the excessive harvested rainfall of this month plus the leftover from last month. So we get total of 0 or 3 or 3. At month May, we have excessive harvested rainfall 444 meter cube. The leftover is 747. If we plus these two values, it's already over the tank volume. The tank volume provided is 850. So the program will take the minimum value of these two. And at the month June, the harvested rainfall cannot meet the water demand. So the water stored inside the tank will be started to be used up. So which is 850 minus 276. So the left is 574. We look at all the calculation for each month and why we choose 850 as the tank storage volume. Because when it arrived to the month October, the water being left inside the tank is only 1 meter cube. So the tank size 850 is the most optimum. It keeps water at the wet months and use them at the dry month. The tank is not oversized. This case is the case where for every month the water demand can be satisfied. There's another scenario. We have another algorithm to handle that scenario, which the harvested rainfall cannot meet the water demand for each month. For some month, the tank storage volume will be 0, because no matter how we increase the tank size, it cannot store the water anymore. We will look at that scenario, which happened at month April. This is another scenario where the harvested rainfall cannot meet water demand, no matter how we increase the tank size. This is month April, so the empty tank will start at month April. It means it represents the owner installed the rainwater harvesting system at month April. So we look at month May. Excessive harvested rainfall is 444. So the tank will store this amount of water. At month June, it already entered the dry months. The harvested rainfall cannot meet water demand. So the water inside the tank started being used up. The amount of water being stored inside the tank is 444. Then started to happen is the dry months. If we sum up all this negative value, we can see that all the negative value here is larger than the 444. So it means no matter how we increase the tank size, it cannot meet the water demand. So the tank size will not be increased anymore. It will stop at 456. 456 equals to the estimated water demand. The tank size will start at 456. And if this scenario happens, the scenario as the month April happened, the program will stop the iteration. It will not increase the tank size anymore. So these are the two algorithms we implemented inside the software in order to get the most optimum storage volume. I will now proceed on to rainwater housing tank design using Poncat. There are 4 steps involved. The first step is to key in the rainfall data. The rainfall data needed is the average monthly rainfall from January to December. The data need to get from the GPS. So I will just copy the value from Excel and paste them into Poncat. I paste the value in. Say these are all the average monthly rainfall. I key in. And the average yearly rainfall, this one, which is summing up all the average monthly rainfall, we get the yearly rainfall. After this step, we proceed on to harvested rainfall. Rainfall can be harvested through 3 means. The first one, the most common one, is the rooftop catchment. The second one is from impervious pavement catchment, can be car park. The last catchment can be landscape catchment. Let's say our case is a hospital and the rooftop is 600 meters square. The area must be plain area. If the roof inclined, we have to take plain area. Same for all the other catchment. The catchment area must always to be plain area. So say the hospital rooftop is 6,000 meters square, and the runoff coefficient, which represents how effective the catchment is in capturing the rainfall. There is a table here. The default value here is recommended by the MASMA second edition draft. Say I choose other material. If the roof material is unknown, we can choose others. Once I click, the value 0.75 will be copied into the cell. If I want to change the value, still can. So we will skip this one and this one. We assume the rainfall is harvested through rooftop only. After that, we key in the average days per month. Say I key in 30 days and click calculate. That's it. I proceed on to water demand. The water demand here means non-potable usage, like toilet flush, washing dish, watering plants, washing cars. It's not for potable usage, but for drinking purpose. As I click here, there are several selections. The selection here is actually come from the parameter. And the value here we taken from table 6.1 of Masma second edition draft. It gives types of appliance, types of usage, whether indoor or outdoor. If indoor, it could be toilet flush, washing machine. If outdoor, it can be watering the plants or washing cars. Different purpose, different application. So for the toilet usage, it has 2 units, liters per flush or liters per day. And the average water use, the value here, is from the table 6.1. If you want to change, we can just double click and change it. If we want to add, we can manually add or delete. So after this parameter is complete, then we can choose the appliance we want. So let's say I choose toilet dual flush, unit I choose liter per flush, and the average water use will be taken out from the parameter, and then I need to specify the frequency of use per day. Here the unit I choose is liters per flush, so I need to estimate one day got how many flushes. This is a hospital. Let's say I assume 4,000 flushes per day. The total usage will be 4,000 plus times 3.8. So we get this value. Depends on how many types of appliance we have. We can still add on, and the software will add up all the usage. This one is for the indoor, and this one is for the outdoor. The outdoor input technique is exactly same as the indoor. So I will skip the outdoor and proceed on. Here, the software calculates average daily water demand, monthly water demand, and yearly water demand. As I click the button calculate, it will give the value of required storage of the tank. The most optimum storage volume. And I proceed on to tank sizing. This one is optional, so I can choose either rectangular or circular. Let's say I choose a rectangular tank to be put on top of the roof of the hospital, and I specify the dimension I want, say 15. And I click calculate, and this will be the total provided tank storage. And I click on button analysis. The software will generate 3 types of output: texture report, summary report, summarize the important design result from texture report, and the graph. This graph is the average monthly rainfall. And this graph is the graph which we looked at just now, the case 1. So that's all for PointCat demo. Thank you.